Hey, welcome to the 5th video about thermodynamics for IB Physics. In this one we're going to be looking at PV diagrams. Now PV diagram is a graph where you plot volume on the x-axis, pressure on the y-axis, and a point on the graph shows you the state of a system. So if you know the pressure and volume of a gas at a particular point in time, you plot it there. Now, if the pressure and or volume of the gas changes, what's going to happen is that the final state of the gas will be in a different location. In this case, if this is the initial and that's the final, the pressure has decreased and the volume has increased. And we can also, in order to go from this pressure to this pressure, it needed to get there somehow. And we can draw the path that it takes on the graph. And that path can take many different shapes, and there are some special ones you need to know about. So I'm going to remove that for now. The first kind of process, and so this is our list of processes here that you need to know about, is an isobaric process. In an isobaric process, the pressure is constant. Iso is Greek for the same. Baric is the word we use for pressure. It's the root of barometer, that which measures pressures or bars. And in isobaric process, the pressure stays the same, and so that is represented by a horizontal line. Now, the useful thing about isobaric processes is that the work done is equal to P delta V. They're the only ones where you can use that equation. An isochoric process is the next one you have to know about. And in that one, it has constant volume. Sometimes these are called isovolumetric processes. On the graph, the isovolumetric process is a vertical line, not like the one I drew, like that one. And in an isovolumetric process, the pressure can increase or decrease, but the volume doesn't change. And the result of that is that the work done in an isovolumetric process or an isochoric process is zero. So delta V is zero, therefore work is zero. An isothermal process is one where the initial and final temperatures are the same, or it's where the temperature stays constant. And in an isothermal process, if you have a constant temperature at an ideal gas, that means the product of pressure and volume is a constant, which means that it's going to follow a curve that looks like this. I'll redraw that. Basically, it's y equals 1 over x. And we call the line of all points that have the same temperature an isotherm. Okay, there we go. And because you've got constant temperature, one consequence of that is that the internal energy, which is related to temperature, is zero. So if the temperature stays constant, your internal energy stays constant as well. The last kind of process you need to know about is an adiabatic process. And in an adiabatic process, no heat is added or taken away. So Q equals 0. And an adiabatic process also follows a curved line, but it's going to be steeper than an isotherm. So if you have two curved lines on a graph, you're told one is an isotherm, one is an adiabat. The steeper one's the adiabat. And we'll look a little bit more at why adiabatic is special in the next video. But you need to know these 4 special kinds of processes. You need to know how they're defined, you need to know how they look on the PV diagram, and you need to know the special mathematics for each one. Now, in order to make anything useful with an ideal gas, you need a closed cycle. You need the gas to return to its initial state. So you might have a cycle that looks like this, where you have, the arrows all need to point the same direction, where first you have an isochoric compression, or an isochoric pressure drop. You have an isobaric expansion. This might be an adiabatic compression, and this might be an isothermal compression, whatever. And anyway, you have a closed cycle. And if you look at the work that is done, I'll call this in step 2, label as 1, 2, 3, and 4. The work done in step 2 is that blue hatched area. But if we look at the work done in steps 3 and 4, that's the orange hatched area. But because it's being compressed in one part of that cycle and expanded in another part of that cycle, the result is that the net work done in the entire loop is equal to the difference between those two, which is to say the area enclosed inside that cycle. And that number will tell you the work done in one cycle of the engine. And I've called it an engine because closed cycles are either refrigerators or heat engines. And I'll explain a little bit more about that in class. But the work done is the area enclosed in one cycle. You need to know that. Now, what a heat engine is it's usually represented as a circle. It's something where heat comes in. You have a high temperature reservoir here. Sometimes called a hot reservoir. It's at temperature TH. You have a cold temperature reservoir here at temperature TC. What the heat engine does is that it takes a certain amount of energy, QH, from the high temperature reservoir, turns some of it into work, and the rest of it gets expelled to the cold temperature reservoir. Conservation of energy says, or the first law of thermodynamics, says that QH, the heat in, equals the energy out, which is W plus QC. Strictly speaking, conservation of energy doesn't require that. But what conservation of energy does require is that if the engine doesn't, gradually freeze, or the temperature increases to the point where it explodes, so if the temperature of the engine is staying more or less constant, that needs to be true. Memorize that. Very important. And also, there's the idea of efficiency. A really useful engine, for all the energy you put in, will get most of that out as work and not have to lose very much heat to the cold reservoir. And we define efficiency as W divided by Q in. You need to know that. There are some limitations on how great the efficiency can be, and we'll see those in the next video, but for now you just need to know the definition. And last of all, let's say that we have a work done in one cycle of an engine. It does 68 joules in one cycle. The power output of the engine is 4,500 watts. The question is, how many cycles are there in 1 minute? So 1 watt is 1 joule per second, and so power is 4,500 joules per second. And in order to get 4,500 joules, we need a certain number of cycles in 1 second, and that's going to be 4,500 joules divided by the number of joules in each cycle is 68. And that means this operates at 66 revolutions per second, 66 cycles per second, which, if we multiply by 60, tells us that the number of cycles in 1 minute is 3,970. So roughly 4,000 RPM. To get more power, you run at higher revs. That's why, in car engines, power generally increases with the number of revs per minute. And now let's say that during every cycle the engine takes in 210 joules of heat. If this is, say, a lawnmower engine, that heat comes from burning gasoline. If it's a steam engine, it comes from burning wood or coal or oil. But it takes in 210 joules of heat in each cycle. What is the efficiency of the engine? Well, the efficiency is the work out, which in 1 cycle is 68 joules, divided by the heat that is put in each cycle, which is 210 joules, and that works out to be 0.32, which is 32% efficiency, which is about par for the course if this is an internal combustion engine. So for this video, what you need to know is how to read a PV diagram, how to recognize the 4 special kinds of processes: isobaric, isochoric, isothermal, and adiabatic. You need to know what a heat engine is. You need to know how to apply conservation of energy to it. And you need to know the definition of efficiency.